When the United States sails from New York to London, the entire Atlantic Ocean is actually disturbed by the ship. Similarly, an airplane in flight disturbs all the Earth's atmosphere. Intuitively, however, we feel that only a small part of the ocean is important to the ship and a small part of the atmosphere to the plane. Here, a thin plate is towed longitudinally through a tank of very viscous liquid at slow speed. Observe that all of the particles in the field of view are set in motion, although with decreasing speeds far from the plate. Now the plate speed has been increased, yet the particles far from the plate no longer appear to move. Actually, they are moving at least as fast as in the previous scene, but the camera speed has been increased to prevent blurring the action near the plate. The lengths of the red lines are proportional to particle speed. It may be reasoned that there is some fluid particle speed, so slow compared to the plate speed that particle motions at slower speeds may be entirely neglected. This speed is usually taken as about 1% of the plate speed. If a bounding line is drawn to include the fluid particles whose speed is 1% or more of the plate speed, the region bounded by the line is called the boundary layer. You are now moving with the plate so that the undisturbed fluid appears to be moving past the plate. The lengths of the red lines are still proportional to the relative fluid speed. The boundary layer is identical with the previous case, but it now has to be defined as the region within which the fluid speed is less than 99% of the apparent stream speed. The boundary layer grows thicker with distance from the leading edge. The growth rate is not linear, however. The boundary layer becomes thinner if the velocity is increased. If the viscosity is decreased, if the density is increased, or if their ratio, the kinematic viscosity, is decreased, the boundary layer also becomes thinner. When these factors influencing boundary layer thickness are combined, we find that the dimensionless boundary layer thickness, delta over x, depends inversely on the Reynolds number formed using the distance x from the leading edge as length parameter. By theoretical calculation, delta over x is approximately equal to 5 over the square root of Reynolds number. In air, boundary layer development is the same as in liquid at the same Reynolds number. Identical laws hold for all fluids, whether liquid or gas, at least as long as the fluids are incompressible. Boundary layer velocity profiles are produced by shear action between adjacent layers of fluid. The magnitude of the shear stress is given by Newton's law of viscosity. shear is eventually transferred to the plate surface, where it is felt as drag or skin friction. Theoretical calculation of dV by dy at plate surface permits evaluation of the wall shear stress at each x distance, and drag is obtained by integration over the plate of length L. Drag is conveniently expressed in terms of a dimensionless skin friction coefficient, C sub F, and this coefficient is a function of Reynolds number only. The flows we have been looking at are laminar flows, but laminar flows and their associated theoretical formulas cannot be extended to arbitrarily large Reynolds numbers. Rather, the boundary layer becomes thinner at a given x distance as the velocity is increased or as the viscosity is decreased. And the shear stress or friction at the wall increases until the boundary layer bursts into turbulence. Turbulent flow is characterized by random whirls or eddies as opposed to the smoothness of laminar flow. Turbulent, laminar. Watch the boundary layer become turbulent as the plate is towed past the camera. Again. The upper boundary layer in these pictures has been made turbulent by placing sandpaper on the plate surface to create a disturbance. The lower boundary layer is still undisturbed and laminar. Turbulence can be generated in the boundary layer by disturbances only if the X Reynolds number is greater than about 100,000, so that close to the leading edge, the boundary layer must always be laminar regardless of disturbances. A transition region of intermittent turbulence connects the laminar and turbulent portions of the boundary layer. Observe that the flow outside the boundary layer is undisturbed and laminar. But even if the outside flow were turbulent, a laminar boundary layer would originate near the leading edge, becoming turbulent later. Outside disturbances influence the location of transition. By carefully avoiding disturbances, transitions can be delayed to Reynolds numbers of several million. Here, a turbulent river flows over a dam. A boundary layer originates on the concrete surface at the top of the dam, becomes turbulent, and thickens until it reaches the water surface where it becomes visible, because the small, intense eddies of the boundary layer turbulence entrap air from the atmosphere. The original river turbulence is invisible because its eddies, which originated on the riverbed far upstream, have decayed. A turbulent boundary layer is thicker than a laminar boundary layer at the same Reynolds number, and velocity profiles are much flatter in the turbulent case. shear stress is no longer given by Newton's law of viscosity. Between the turbulent fluid and the plate, too close to be seen clearly in the picture, there is still a laminar sublayer in which shear stress can be calculated by Newton's law. Velocity gradients and shear are very large in the sublayer, so that the skin friction coefficient exceeds that for a laminar boundary layer at the same Reynolds number. Since the boundary layer near the leading edge of a plate is laminar all of the time, the integrated drag on the plate is made up partly of laminar and partly of turbulent friction after the boundary layer becomes turbulent. Because transition depends on the disturbances that are present, there may be more than one value of the skin friction coefficient for a given Reynolds number. However, when transition occurs near the leading edge of a long plate, friction of the laminar part is negligible compared to that of the turbulent part, and there is a unique relationship between skin friction coefficient and Reynolds number. Boundary layers also develop in the entrance region of a pipe. Leaving an undisturbed core in the interior of the pipe. The boundary layer grows to the center of the pipe, and the core disappears as the fluid moves downstream. There can be no further growth thereafter, and the boundary layer or flow is said to be fully developed. These pipe velocity profiles have been produced by laminar flows and are typically parabolic in shape. Pipe flow, too, becomes turbulent at large Reynolds numbers when disturbances exist. And the velocity profiles are much flatter. Near the entrance of a pipe, however, the boundary layer is always laminar, just as in the case of a plate, regardless of whether the core flow entering the pipe is laminar or turbulent. Transition to turbulence occurs in the developing boundary layer. And turbulence in fully developed pipe flow is a result of this transition. Most fully developed pipe flows at Reynolds numbers greater than 2,000, the critical value for pipes, are turbulent. Fully developed pipe flow is always laminar when the pipe Reynolds number is less than this critical value. It may be laminar at larger Reynolds numbers if disturbances can be prevented in the developing layer. Observe the effect of a disturbance on the developing laminar boundary layer at a high Reynolds number. When the disturbance is removed, the flow is laminar again. Disturbance in. Disturbance out. The distance required for a pipe boundary layer to become fully developed is known as the entrance length. In turbulent flow, 50 or less pipe diameters are usually required. For laminar flow with smooth entrance, about 58 diameters are required at a Reynolds number of 2,000, and entrance length is proportional to Reynolds number. In a pipe, frictional resistance in the boundary layer appears as pressure drop or as head loss. Increasing the velocity increases the loss. Head loss depends not only on velocity, but also on several other factors, including pipe diameter and length of test section. These are usefully grouped into two dimensionless quantities, pipe Reynolds number and friction factor F. For smooth pipes with fully developed boundary layers, friction factor is a function of Reynolds number only. Fully developed laminar flow has been used to produce these examples. Theoretical evaluation shows that for circular pipes in laminar flow, friction factor equals 64 over the Reynolds number. Had some of the entrance length been included in the measurements, frictional resistance and F would have been larger than in the fully developed case illustrated here. Head loss and friction factor are always greater in turbulent than in laminar flow, other factors remaining constant. Head loss continues to increase with velocity after the flow becomes turbulent. But friction factor again drops with increase in Reynolds number. Experimental data for fully developed turbulent flow in smooth pipes, no matter how large the Reynolds number, are correlated by a single line on the friction factor versus Reynolds number diagram. Boundary layers do not always remain attached to the surfaces on which they are generated. When the pressure rises in the flow direction, fluid particles near the wall, having already consumed energy to overcome skin friction, do not have additional energy to overcome the pressure rise and to continue their motion. By leaving the wall, however, most particles do manage to keep moving. The boundary layer is then said to be separated. A circular cylinder has been selected to demonstrate typical effects of separation. The cylinder is towed past the camera. And here the cylinder and camera are towed together. The boundary layers separate alternately from opposite sides. Observe that the boundary layers are laminar up to separation, as is the outside flow in this picture. The region between the separated boundary layers is called the wake. Even with a turbulent outside flow, the cylinder boundary layer and wake would have been laminar at this Reynolds number. Alternate separation from opposite sides of the cylinder persists over a wide range of Reynolds numbers. As Reynolds number increases, the attached boundary layer remains laminar while the wake becomes turbulent, and the turbulence moves closer to the cylinder. Similar separation occurs on all other blunt bodies. regless of fluid. Swaying telephone wires and suspension bridges are manifestations of alternate boundary layer separation. Separation is absent only during the first moments after motion starts, or at extremely small Reynolds numbers in steady motion. At slightly larger Reynolds numbers, symmetrical separation and a closed wake appear, but by the time Reynolds number reaches 100, the alternating separation pattern is established. Pressure distribution on a cylinder is associated with the flow pattern. From the front stagnation point to near the 75-degree point, the pressure falls continuously at this Reynolds number and is in rough agreement with ideal fluid theory. But from here on, whereas theory requires the pressure to recover its value at stagnation, separation prevents recovery. When the pressure is resolved in the direction of motion, a net pressure force or form drag results. This is in addition to any skin friction drag occurring where the boundary layer remains attached to the wall. For the circular cylinder, form drag far exceeds skin friction drag at all but the smallest Reynolds numbers, and the skin friction can be ignored. Again, drag is conveniently portrayed in coefficient form. Drag coefficient for a circular cylinder remains near unity over a large range of Reynolds numbers to well over 100,000. But finally, just as in the case of the plate and the pipe, the laminar boundary layer becomes turbulent. Turbulence re-energizes the boundary layer particles and enables them to travel farther along the wall before separating. Observe the reduction in wake area associated with transition. Pressure recovery in the wake is more complete with a turbulent boundary layer. Higher pressure and smaller separated area in the wake produce a marked decrease in form drag when a turbulent boundary layer exists. Reynolds number at transition, shown here between 4 and 500,000, actually depends on the disturbances in the stream and on the roughness of the cylinder. Except for the uncertain region near transition, form drag coefficient is a universal function of Reynolds number for the circular cylinder and for other blunt bodies. Many practical problems, such as flows about airfoils or pump blades, involve both skin friction and form drag. Little or no separation occurs on a thin foil at small angle of attack, and the drag is largely attributable to skin friction. It is roughly the same as that of a plate at the same length Reynolds number. But separation sets in when the angle of attack increases, and form drag becomes predominant, increasing the drag coefficient considerably. So far, we have dealt with smooth surfaces. Rough surfaces are often encountered, and these may have two effects on boundary layer flow. First, the roughness disturbs the flow, and if the Reynolds number is large enough, it promotes transition to turbulence. Thus, in a certain range of Reynolds numbers, even a few roughness particles may serve to increase the head loss. Or drag, where these are largely frictional. Or, on the other hand, may serve to decrease the drag when drag is largely due to separation. Second, roughness particles have form drag of their own, and this drag may add to the total surface drag. Observe the effect on pipe head loss of introducing a rough surface. With rough surfaces, drag coefficient and friction factor no longer depend on Reynolds number alone, but also on the roughness characteristics. Important characteristics include the size, spacing, shapes, and uniformity of the individual particles. These characteristics are usually represented by a single linear dimension called the equivalent roughness height, H. H is often measured with respect to the boundary layer thickness. It is not always equal to particle height, as shown here. Depending on the roughness characteristics, friction factor in fully developed pipe flow may increase with Reynolds number, decrease with Reynolds number, or remain constant. A similar range of possibilities also exists for the drag coefficient of a plate. This is a standard pipe friction factor diagram. It is based on the averages of a great many experiments on various sizes of pipes with different kinds of surfaces. Equivalent roughness height is expressed in terms of pipe diameter here. Such a diagram is accompanied by a table of equivalent roughness height. Since height is only one of several characteristics of surface roughness, and the chart is based on the averages of many different surfaces, any given experiment, especially when uncommon surfaces occur, may differ considerably from the values given by the chart. The two limits of each curve of constant relative roughness should be noted. For high enough Reynolds number, the friction factor becomes constant. Flow with constant friction factor is known as fully rough flow. On the other hand, at small Reynolds numbers, roughness tends to be submerged in the laminar sublayer, and the flow acts as though it is effectively smooth. In between, the flow may be called partly rough. Similar standard charts for the drag coefficient of a plate are also available.